Hey y'all, it's Becca. I am a math, physics, and astronomy tutor here at Chegg. If you need such a tutor, feel free to hit me up at my profile below. But today I'm going to talk to y'all about light. Obviously, light is something that we encounter on a daily basis, but there are a lot of fun little characteristics of light that you can talk about in your physics or chemistry or physical science courses. So first of all, when we think of light, it's not necessarily just the light that we see around us, the visual light. In fact, visual light only accounts for a small percentage of what we call the electromagnetic spectrum. Now, the electromagnetic spectrum, or the EM spectrum, is a way that we can kind of classify the different kinds of light that we see, or that we don't see, based on their energies, their frequencies, and their wavelengths. So you'll notice in this little sketch of waves right here, we think of light as a wave sometimes. We also think of light as a particle sometimes, which is kind of funny. Einstein was one of the first people who recognized that light can be recognized as both a wave and a particle. It has both wave and particle characteristics. But if we represent light as a wave, we can think about all the different kinds of light that would represent such a wave. So you can see that the wave length, or the width of the wave, we call it the wavelength, decreases as we move along the spectrum. And what that means is that the frequency of the wave actually increases. The frequency is the amount of times that the wave can propagate in usually 1 second or some length of time. So down here on the left-hand end of the spectrum, we have radio waves. Now, radio waves are pretty low energy. The longer the wavelength, the lower the energy, turns out. And the lower the frequency as well. So down here in radio waves, we have wavelengths that can be about 1,000 meters long. We don't think about that usually. How can a wave of light be 1,000 meters long? That's so long. But radio waves, we don't see, so we wouldn't really think about it. But they have wavelengths of 1,000 meters. And the frequency of a radio wave is about 10,000 hertz, and a hertz is inverse seconds. Next on the list, we have microwaves, we have infrared waves, and then finally we're in the visual spectrum, which is a very small bit of the spectrum that we can see. Those are all the colors of the rainbow. Then moving higher in energy, we have ultraviolet waves. Those are emitted by the sun. They cause us to have sunburn. And we have X-rays, which of course we know can penetrate our skin, but not our bones. So we can get X-ray images of ourselves that show our bones. And then all the way up here are gamma rays. Now, gamma rays are very high frequency, high energy, low wavelength waves. Gamma rays, instead of having a wavelength of 1,000 meters, have a wavelength of 10 to the minus 12 meters. That's just a tiny, tiny, tiny fraction of a meter. These are tiny little wavelengths, and they're very high energy and very dangerous if you're ever exposed to gamma rays. The frequency, however, is very high. Where we have 10,000 hertz for radio waves, we have 10 to the 20 hertz for gamma rays. That means a 1 with 20 zeros after that. That many of those waves can propagate in 1 second. So crazy high energy waves, very dangerous. So how do we figure out how fast a wave is moving? Well, it turns out another thing that Einstein is famous for recognizing is that the speed of light is constant in a vacuum, and it's constant, and that's really, really important to physics, especially to quantum physics. Einstein's theory of relativity essentially rests on the fact that the speed of light is constant, and we call that quantity c. Now, it is a speed, and in SI units, the units for velocity are meters per second. So if we have a velocity in meters per second, and we have a wavelength. Now, wavelength is a unit of measurement of distance. So in SI units, our distance units are meters. And frequency, we call that the Greek letter nu. Oftentimes you may see it represented as F. That's fine as well. For the purpose of this video, I'm going to represent it as nu. Nu is given in hertz, but a hertz is actually just an inverse second, so it's equal to 1/second. So from this dimensional analysis, we can see that if we want to relate the speed of light in meters per second to wavelength and frequency, all we have to do is take our wavelength in meters and multiply it by our frequency, which is in inverse seconds. Because dimensionally, meters times 1/second gives us meters per second. So from that, we know that c is equal, the speed of light is equal to our wavelength times our frequency. Now, if we want to solve for each one of those variables, just in case we need to, let's solve for wavelength. If we were to get wavelength by itself, we would simply just have to divide both sides by frequency. So wavelength is simply speed of light divided by frequency. And to find frequency, you do a similar thing. To get frequency by itself, this nu by itself, you would have to divide both sides by lambda. This is the Greek letter lambda right here, represents wavelength. So your nu would be c divided by lambda. So if you're ever trying to isolate one of those quantities, it's really important to recognize that the speed of light is constant and is related to the wavelength times the frequency. Okay, so let's see if we can expand our understanding of light into the particle interpretation. Now, a particle of light is called a photon, and it is one quantum of light. Now, quantum just means one little packet. One packet of light is called a photon. And the energy of a photon is very fundamental to the study of quantum mechanics. So if you're doing a little bit of intro to quantum mechanics, you may have heard of this guy named Max Planck. Very important in the field of quantum. He discovered this proportionality constant right here. This is called Planck's constant, and it's denoted by the letter H. And what it does is it helps us scale everything down to just one quantum. And in this case, it's a quantum of light, a photon. So let's say we were trying to find the energy per photon. Well, it turns out energy of light is given by this proportionality constant H times the frequency, H nu. And what if we didn't have the frequency, but we had the wavelength? Well, reviewing the ways by which we solved for each of these variables here, lambda, nu, using the speed of light as a constant, we know that nu is equal to c over lambda. So you may also recognize this formula for energy as our proportionality constant H times, well, nu is c over lambda. So hc over lambda here. Okay, so suppose you were asked to find the energy of a photon that has a wavelength of 500 nanometers. Now, a nanometer is 1/1000th of a meter. So the first thing we'd have to do is convert this wavelength into meters. So we have 500, and a billionth is 10 to the negative 9th. Okay. Everything else, turns out, is a constant that we know, either h, Planck's constant, or c, the speed of light. We know that the speed of light in a vacuum is roughly 3 times 10 to the 8th meters per second in the correct units. And our Planck's constant is 6.63 times 10 to the negative 34 joules times seconds. Now, joules are our unit of energy. And we'll find that if we solve for energy, we have our h in joule seconds times our speed of light in meters per second divided by our wavelength. I'll just do this in symbols first. Our wavelength, which is in meters. So notice that the seconds up here cancels with the seconds down in the denominator of this, meters per second. Meters in the numerator here cancel with the meters down in the denominator, and we're left with joules, which conveniently is our unit of energy. So all you would have to do here is plug in our values for Planck's constant, for the speed of light as well. And in the bottom, our value for wavelength. Now be careful when you're working with scientific notation. It can sometimes be tricky to enter into a calculator. But once you pop that into a calculator, you will know the energy of 1 photon of light at that wavelength in joules. Okay, so this is a little bit of an intro to light, how it can be denoted as a wave, how it can be denoted as a particle, and how we can find out some of the characteristics of that light using both Planck's constant and the fact that the speed of light is constant. I hope you all enjoyed this intro. If you need any help regarding the speed of light, feel free to hit me up or any other physics tutor here on Chegg. Bye!